In this video, we are going to take a look at how to do a data reduction. The first thing we're going to do, as always, is we are going to check the communications just to make sure that the instrument is communicating with the instrument. We see here that it is. From here we'll close out. And the manual that Kat sent to me suggests that we do a backup at this time. So to do that, we go to channel list, and the English is much improved this time around. It still takes a little bit of interpretation. What we're going to do is we are going to read everything from the 920. And there's the first one, and the rest will populate in a moment. Okay, there we go. And here we have all the various things that I've loaded into the instrument over time. We are going to predictably be working with this one, which I've called test, which means we can get rid of it if we absolutely must. And save it, and we're going to save it for all channels, and it'll automatically take you over here to this directory, and we're going to call this test, and you can see there's a save here, just like everything else. Okay, so now that we've got that saved, we can close out. And the next thing we're going to do is we're going to go into calibration, which we see here. And this is very similar to the screen we've seen prior. Okay, and this time we're not going to collect up new measurements. We've seen that in the past. This time we are going to open up an existing file. And here I have a ground beef with constituents, and CLD is the extension that they use. And we're going to use that one because I've already loaded the constituent values in. And here we go, and we see the dates and the sample IDs, and it looks like we have 64 of them. The manufacturer recommends a much smaller number of samples, as few as about 15 or 20. I have a hard time getting to that. And on this one we had 65, and you can see we have the constituents. These are fat and moisture. There seems to be no way to change these names right now. I hope that changes in the future. And you can see the date and time where they were collected. And if we slide off to the side, you can see the raw absorption values. Okay, from here, if we look at that, we see the calibration data. And if we take a look here, we can see the spectra. And again, this is a count value, which we're a little bit foggy on, and the raw absorbance, which we have here, and the second derivative. And this basically shows kind of where the action is on at the different wavelengths, and kind of the more range you see here, I believe, is where the most change is taking place. And over here, we can see the area that we want to reduce over, and just like everything else, you use the pull down menu, and it'll let you pull a range. It won't, or does not seem to allow you to select individual wavelengths as you would in an OWLS calibration. Perhaps that'll change in the future. We see here we have the components as we would on our own instruments, 1, 2, 3, 4. These being basically labeled, hard labeled, moisture, protein, other, and other. We're going to do component 1 because that's fat, and then we click on execute, and now the computer is going to go to work, and it's going to generate a model for us. And here we go. And these factors, I'm not entirely clear on what these are. I think these are the inflection points where it is measuring the differences from each other. And we see here that we're using the second derivative. I believe it auto selects for which one fits best. And over here we see the standard, the predicted, the residual, all this kind of thing that we typically see. There we go, there's one. If we're lucky, we'll spot one that's really, really far off. In this case, it's sample number 29. We could go back and remove 29, but then it would no longer be sample number 29 because it would just reorder everything. That's something that I hope we can fix a little bit later on, certainly if we're going to use the same set, set of samples for everything. Again, residual error, predicted. And once we have these, we can save them. We see them as a COE. I'm not going to bother saving it, but you can see what that'll look like. And I'm going to move over to the coefficient graph. And this is showing us the importance of the relative importance of the individual wavelengths to it, which is something we're going to have to work on understanding intuitively a little bit better. And over here we have a much more familiar calibration graph. And all this should make a lot of sense. It does the same sort of things ours does. It lets you click on them. Now we see the outliers over here, the high fat samples. I think these might be moisture samples. Anyway, we see the lab down here, the predicted up here, and we see the standard, the kind of comparative statistics we've seen before. It's agreeing at 0.93, the standard error is 2.1, there's 64 samples, and the number in sample group is 63. I'm not quite sure what the difference is here. And we can save, we can't save them, we can print them if we like, and that's pretty much a quick tour of it. And the next step of it would of course be to find the outliers, go back, reduce without them, as we do normally. There is no real way to owls these as we do in ours, and I don't think there's a good way to reduce with repeatability in mind. We might be able to work that into subsequent versions of the software. In the meantime, loading up the values that we just saved earlier will be shown in another video. Thank you. I hope this has been helpful.